Yeah, I mean, you just need to know that you need to do it. Otherwise, it's weird.
So we're gonna do Thursday then?
Yeah. Yeah, no,
That's been greasy notes.
Greasy notes? We'll bring them to the exam. Everyone will know here at the pizza.
Oh yeah, pizza day.
You'll have those fond memories while I ream you with horrible questions that, trying to give with one hand and take with the other. Okay, so we've been using Lagrangians for a couple of lectures now. I've been avoiding the nitty-gritty, to be honest, at the beginning, because I wanted to show you guys kind of how to get a working knowledge of how to actually use them to solve problems first. And now we're going to go a little bit more into the background of why it works, mathematically speaking, and some terms that we are going to use as we discuss Lagrangians, but probably aren't going to get to any examples today. If we have time, I will acquiesce to Jonah's request to do a double pendulum. So that's in the queue if we get through everything else on time. We'll see. We need a lot of extra time for that one. That one's exciting. Okay, so recall we're looking at Lagrangians where we're trying to minimize the path over which action is minimized. Action being the Lagrangian. On the path, yes, whatever it needs to be. Okay, so the way we do that, using the Euler-Lagrange system, was to apply the Euler-Lagrange equations in each case. So let's say you're doing this to just a single particle flying around in 2 dimensions. In that case, the Lagrangian is going to be in terms of those 2 dimensions. Generalize. Go ahead and grab food if you want as I'm going. This is not the formal period. You guys can go ahead and grab more whenever you need to. Don't worry about me droning on up here. Okay. So in general, if we have 2 dimensions, this would be what we'd say the Lagrangian was a function of x and velocity in x, y and the velocity in y. In which case you'd apply the Euler-Lagrange equations and end up with something that looks like dl dx is equal to d by dt of dl dx dot in one dimension. The other dimension, that's going to look like dl dy is equal to d by dt of dl dy dot. Okay. Well, I mean, what does this end up looking like in general? I mean, you just have a particle flying through space. Then Lagrangian is going to be equal to 1/2 m x dot squared plus y dot squared, right? Minus some potential, and we'll assume it's just a function of x and y and not of velocity, so as not to get ugly. I want you guys to, barf up your pizza. It would just be ugly if I had a function of velocity. No one wants that. Okay, so if you take dl dx then, the left-hand side kind of looks like, if you're taking this in both dimensions, this kind of looks like negative del of u. Right? Because this is all that's left. Presumably the kinetic energy is not a function of position, as we've done it anyway. So this is just negative, and then derivative with respect to, partials with respect to x, y, and z are going to end up looking like this. So this will be a u and x since I'm doing it in each dimension individually, but this is what it would look like. Similarly, what's dl dx dot? So this will be d by dt of dl dx dot. In this super simple case, Yeah. Momentum, right? In which case, this becomes, and you get negative del of the potential, which is equal to force, is equal to ma. Okay? So this is not any different than what you've seen before. In fact, the same thing. And in fact, because of what Jonah points out, so we have two different terms here. We have our differential Lagrangian with respect to x, and then we have d by dt of the differential of Lagrangian with respect to y. It's this dl dx term kind of looks like a force, and the dl dx dot term kind of looks like a momentum. You know, kind of. When we start putting this in our generalized coordinates, is it exactly the momentum? Yeah, I mean, in some cases, yes. In some cases, you know, kind of maybe not, but it's close. So we actually call these the generalized force and the generalized momentum. This is for, now that you're junior physicists, that physics 211 approach of actual force and actual momentum, you're above that now. Now we've gone to meta. Okay, this is the meta version of force and momentum, the generalized momentum, and the generalized force. I like this room better than the other room because I can wander up and down the sides. It makes me feel hemmed in to have to stay in front. It freaks me out. So basically, in every problem, you end up with some generalized force and generalized momentum. Remember, one of the issues with doing Lagrangian problems, we said, was that, well, yeah, if you do all the math, it all works out, but like, why does it work out? What is your intuitive feel for it? It's really hard to get that. But this is our attempt to try to get there, is remember that if you're doing these problems, the d by dx term is kind of like the force, and the d by dx dot term is kind of like the momentum. If you need to think of it through that way. So you can imagine, if you need to do this in, say, with two different particles, we've mostly just been looking at individual particles so far. If you have two different particles, then you might look at something where each of them are in 3 dimensions, right? Then we're going to have maybe six different generalized forces and generalized momenta. So say 2 particles, 3 dimensions. You're going to end up with generalized force for particle 1 is equal to the generalized d by dt of generalized momentum of particle 1. And that's going to be true for particle 1 in each dimension. Z1 d by dt of dl dz1 dot. All right, so that'll be 1 particle. If you have 2 particles, you can just keep going here. You just do the same thing, but for particle 2. So back in your heady days of physics 211, we've done this with vector equations, right? So well, the feature and a curse of Lagrangians is that we typically don't think of things in vectors anymore. We abstract them all out into their individual generalized coordinates. And then you don't need to know about the vector part. You can just do each part separately. when you just have two particles in 3 dimensions, notice that 2 particles, 3 dimensions, you multiply those, you get six different equations. That's not always true, but when it is true, your system is called holonomic. So here's some nomenclature for you. Holonomic. So this is actually of great use if you have a holonomic system, because in general they tend to behave better. They're more understandable and they're going to be easier to calculate. An example of like a non-holonomic system the book uses is, imagine you have a ball on a table. Okay, you have a ball on a table, and if everything's frictionless and it just stays there, and you move it around and it just slides, that's no problem. You've got two degrees of freedom, because it's on a table. You got 1 particle. You got only 2 coordinates that you need to describe the whole system, just the x and y positions. Great. If instead you assert that the table is actually infinite friction, right, and so the thing can only roll, so it's rolling and always in contact, then as you roll it around, you can imagine you can put it in a given position, then roll it around and bring it back to that same position, but not have it be in the same state, because it's all funny, it's been rolled around. You don't know where it's at in terms of what's going on. Imagine this was a globe, right? You can roll it this way and then roll it along the equator, or you can roll it around the pole more. And depending on what you did along there, once you move your globe back to the same spot, it's no longer going to be necessarily with north up and zero longitude toward you, or whatever you started with. And so in that kind of a case, you'd need, in the case of the globe, right, you'd need x and y, and I think you'd actually need 3 other numbers to describe the state of the system, because spherical geometry sucks that way. If you have a given sphere, and you want to move it into the coordinates of any other sphere, generally takes 3 different rotations. These are called Euler rotations, and I think I talk about it later in the semester, so I'm not going to go over it too much. But you might call them theta, phi, psi, something like that. In general, so the way I do Euler rotations in my code is do 1 rotation around the z-axis, and 1 around the x-axis, and then 1 around the new z-axis, and then you can get back. So with that combination of 3 different rotations around separate axes, and that's not the only way to do it. You can essentially, there are a lot of different systems with 3 different axes you could do those rotations around. They're all called Euler rotations. If you do those 3, you can actually put that ball back into its original state. But it takes those extra 3 dimensions to be able to describe the state of that system over and above just, x and y. Knowing where the center of mass is no longer is enough. I'm not cruel enough to give you any non-holonomic problems in general. This is just FYI, I'm giving you the easy ones that aren't like this. But when you get into real life, you may not be so lucky. Particle physicists, maybe it's not so bad, because particles, you don't have to worry about, they're symmetric. You can roll them around and you can't tell. Planets, of course, not so much. You kind of need to know where they started. Otherwise, things can get ugly. Okay. So I have this proof that Lagrangian works. Kind of boring, right?
We'll believe you.
Let's do the double pendulum first. If we have time, we'll do the proof. Any objections? Okay, good. Okay, the double pendulum could take us the rest of the time. It's a nice one. Oh yeah. It's I was intimidated the other day. I'm just doing it straight up. I'm still a bit intimidated, but I think it's, we'll just, one of the great things about the Lagrangian is, you don't have to be intimidated. You just follow the steps, turn the crank, you're gonna get there. The answer could be so butt ugly that you wish you hadn't gotten there, but it will work if you just plug in the right things and turn the crank. So that's what we're gonna try. What are the 4 steps you need to solve a Lagrangian problem? What's step 1? Okay, Lagrangian in inertial space. Okay, what's step 2? Generalized coordinates. What's step 3? Yes, we write the Lagrangian in terms of the generalized coordinates. What's step 4?
Use the Lagrange equation.
One in Lagrange. Okay, so those are the steps. Let's consider the double pendulum. So here's some mass m1, and then there's another mass m2 on another massless string attached to the end of m1. So the goal is to figure out an equation that will describe the behavior of this system over time given an initial condition, right? So let me give you the answer qualitatively, right? For small oscillations, this actually behaves pretty regularly and in a fairly predictable and rational manner. Once the amplitudes start to get large, like outside the bounds where sine x equals x, this thing literally goes nonlinear and becomes chaotic. So what the word chaotic means is that if you give it exactly the same initial condition, you'll get the same result. However, if you give it the exact same condition, but there's some small difference, and can you get the exact same condition the first 3 and 2 times? Why not?
Because you're always going to have some small.
Heisenberg will get you, okay? There's going to be some difference, all right? And the difference between those 2 states in a linear system tends to grow linearly with time. So, you look at that, the distance or the difference between those initial states that you started with, and you give it some amount of time, and that grows. You give it some more amount of time, that grows to twice that if you give it twice the amount of time. In a chaotic system, the difference between the initial setup and the second setup that you set to go diverges exponentially with time. It's called a Lyapunov time. What that means is that, instead of giving twice as long, it's not going to be twice as bad. It's going to be 3 times as bad, or e times as bad. You give it another time scale, the linear system will be 3 times as bad as the initial. The chaotic system is going to be, e to the 3 times as bad. So what this means is that in any truly chaotic system, if you give it long enough, no matter how close those 2 systems started in time, the final won't necessarily look like that. The reason is, if you start these, and I wish we had one. Maybe I'll find one next time I teach this class. If you actually give it high amplitudes, the reason is this second one will sometimes, like whip all the way around, and sometimes, they sort of violently and very crazily interact and transfer their energy and momentum back and forth. And it's the nature of that violent and crazy interaction, right? Does this thing almost go all the way around, or does it actually go all the way around? And as those 2 little systems start to diverge, if you cross one of those points where, oh, this system didn't go all the way around and this one did, then boom, the whole thing just flies apart and they become totally different. Our solar system, totally chaotic, turns out. All those people that built the orreries, where all the planets move around on exact orbits and everyone, okay, that'd be great. We think the solar system's stable. And the reason we think it's stable is that it's still here after 4.5 billion years, okay? But it's chaotic. And the Lyapunov time, over which the uncertainty grows by a factor of e in the solar system, is about 10 million years for the inner solar system, maybe more like 20 for the giant planets. What this means is that, if you want to know something like where the impactor that killed the dinosaurs came from 65 million years ago, that's like 6 Lyapunov times, okay? That's a factor of 1,000 in uncertainty. We don't kind of know where the planets were even back then. I mean, 65 million years, they're pretty good. We pretty much know. But too much past that, and our knowledge of where actually the planets are today just isn't good enough. And that lack of knowledge diverges in the past or the future, if you want to figure out what's going on in the future. And it goes exponentially because that system, it turns out, like the double pendulum, is chaotic. And it's amazing that you can get such crazy nonlinear chaotic behavior on such a simple system, right? This is not that crazy. They're just like two things. Why is this so complicated? The answer is, we don't look at it because this is analytical mechanics. But if you were in numerical mechanics, you actually look at what this thing did, it is totally crazy. Similarly with the solar system, it's just like planets that have been orbiting around for 5 billion years. What's the big deal? Well, turns out Mercury is the problem child. There's about a 2% chance that in the next 2 billion years, Mercury is going to go haywire. It seems to be the linchpin, that's closest to falling out. And so if you do simulations, so the way we do these chaotic simulations is, we know where Mars is to within 10 meters or something, which is pretty dang good. But, so you start a bunch of different simulations, all with Mars within different places in your uncertainty bounds. And you run a bunch of those simulations in the future. About 2% of them have Mercury doing something crazy. Sometimes, in one of them it crashed into Mars, in one of them it caused Venus to be ejected from the system, as it got a gravity assist from Jupiter. So, crazy stuff. And it's a 98% chance it's not going to happen in the next billion years. It's probably okay. Your kids will be all right. But it's not 0% chance, okay? It's not that simple deterministic system that we all want the universe. I want the universe to be that way, okay? Quantum mechanics thrive on the uncertainty. But it would be great if you could predict this stuff, but you can't. Okay, so that's my brief aside because there's a whole chapter in the book about chaos that I would love to have time to talk about. Instead, you get that 5-minute spiel. So there you go. There used to be a second course, Physics 322. It was like 10 years ago, at least 10 years ago. Anyway, in which case, yeah, you have the luxury to actually talk about this stuff. And honestly, how do I put this? The stuff I cut out is more interesting than the stuff I left in, right? You guys all have a copy of the book, right? No one's going to admit to not having a copy of the book. But it's this section at the end, the further topics section, nonlinear mechanics and chaos, collision theory, special relativity, continuum mechanics. That's like coupled oscillators. That's this double pendulum stuff. That's really fun. I wish we had a chance to talk about that. But that's not going to be on your physics GRE subject test. This is. So we're going to do this. Even though it's less interesting, it's still cool, but more practical in terms of what you're going to be able to do in the future. But know that there's cooler stuff out there. You might have to read on your own though. Okay, so step 1, write down our Lagrangian. All right, so this is the kinetic energy minus the potential energy in inertial space. So we can use whatever coordinates we want. What should we use? What's this absolute simple dumbest thing we could possibly imagine? No, there's something even dumber than that. Let's just use Cartesian, right? This is not the generalized coordinates yet, okay? Let's just write it down in terms of something we know is going to work. And the reason is because this can get hairy really fast once we start getting into the thetas. So let's stick with what we know is going to work, that the total kinetic energy is probably going to be 1/2 m x dot squared plus y dot squared plus 1/2, m1, 1/2 m2 x2 dot squared plus y2 dot squared. That's unimpeachable, right? That can't possibly be wrong. Okay. I'm pretty sure that's not wrong. Let's back off on the certainty level. Okay. But that's pretty basic. I don't think we can go wrong there. Minus, we are in a gravitational field, so this is going to be m1 g we'll call it y1, and then minus m2 g y2 minus y naught or something. We'll call the resting point of mass 1 the positive y direction. Yeah? And so y naught will be the length of this pendulum. Yeah. It shouldn't matter. This is going to quickly drop out since it's just a constant. Okay. That was step 1. Step 2. Generalized coordinates. What generalized coordinates should we use?
Theta and phi.
Sure. Chase's suggestion of the thetas or whatever, yeah. So the obvious ones here are just these angles. Theta, and Jonah wants to use phi. Okay, I call it phi. I use that version of phi. There's other ones, but that one's easier to write. Computer in LaTeX always wants to give me some stupid looking phi that I really hate. In LaTeX, this one's backslash var phi.
Do you use the phi measured from the y or from the angle of the other one?
This is measured directly from straight down,
Okay.
the way I've defined it. So straight down from the first one is going to be the location of the second one. And we'll insert, we're going to need to know the lengths of these pendula. Let's do L1 and L2. And so this becomes L2. Minus a minus L2, so it's going to be plus. It doesn't matter, it's a constant, it's going to drop out. Okay, so we've decided to go with theta and phi. All right, that's not bad. Here's where it gets bad. All right, let's figure out our Lagrangian in terms of then theta and phi. In order to do that, we're going to have to figure out x1, y1, x2, y2, x1 dot, y1 dot, x2 dot, y2 dot. All, actually we don't need x and y. We don't need x, we just need the y's. So we're going to have to figure out what those all are, you know, in terms of these. So let's, on the side, in order to do this part, let's calculate those. Okay. So, x of particle 1. What's the x location of particle 1 going to be?
L1 sine theta.
Yeah. L1 sine theta. And what's its y position going to be?
L1 cosine theta.
1 minus cosine theta? It's 1 minus cosine theta. The way I've defined it, right?
Yes, yes.
L1, L1, 1 minus cosine theta. Okay. Then that's not too bad. X1 dot then is going to be, all right, I know what I think it is. What do you guys think it is?
L1 cosine theta.
L1 cosine theta times,
Theta. Theta dt.
yeah, theta dot. Right? This theta itself is changing with time. So this is going to become L1 theta dot, and the side is cosine. Okay. Not too bad just yet. Y1 dot then is going to be, no one cares about that, it's going to drop out. It's minus L1 cosine theta. This is going to be a plus L1 theta dot sine theta. Is that right?
Yeah.
Okay. Not too bad. That was the easy one. As you can imagine, x2 gets a bit hairier because x2 is going to be x1 plus its own section, right? So the origin of the coordinate system keeps changing because that second pendulum is attached to the first pendulum, which is kind of a pain. And it's going to get even hairier once we get to x2 dot, but we're not there yet. So let's leave that. Okay, y2 then is going to be equal to y1. Yeah. L1, 1 minus cosine theta.
Minus L2.
Minus L2 cosine theta.
Yeah.
Phi, cosine phi.
Yeah.
Yep, minus L2 cosine phi. Okay. Here's where the fun continues. Okay, x2 dot then is going to be equal to the derivative of this, which is x1 dot, right? So that's just the L1 theta dot cosine theta we already know and love, plus L2 phi dot cosine phi. And then y2 dot is going to be equal to y1 dot L1 theta dot sine theta plus L2 phi dot sine phi. Does that sound right?
Yep.
Okay. Note, I have no notes for this, okay? So we are on uncharted ground here. So you guys gotta keep me pointed straight, otherwise this is gonna go off the rails real fast. All right. Now we have what we need in order to plug that back in up here and figure out the Lagrangian in terms of our new generalized coordinates theta and phi. Back to work. Okay, so this is going to be 1/2 m1 x1 dot squared. So that's L1 squared theta dot squared cosine squared phi plus y1 squared L1. Did I do? I said phi, but I wrote theta.
Yeah.
I think I just misspoke. I didn't miswrite, so that's good. L1 theta dot sine squared theta. This is squared. They're all squared. This is a y dot squared. Okay? Plus 1/2 m2 x2 dot squared. Now's where it really comes home. Okay. Whew. Yeah, that's gonna get ugly. Let's do that on a different line. It's gonna be so bad. Continued.
Oh, that's not that bad.
This is the part in your physics career where I want to teach you that, oh, the solution takes 4 pages of algebra. Thank goodness, it's almost done. We just have to go through the 4 pages of algebra and we're there. Don't, you can be intimidated, but press through those 4 pages of algebra because that's really not so bad in the grand scheme of things. No longer do we have the problems where all the, thetas drop out to 0. You do the whole thing in 3 lines. Okay. M2 times x2 dot squared. So that's going to be L1 squared theta dot squared cosine squared theta plus 2 L1 L2 phi dot theta dot cosine theta cosine phi plus L2 squared theta dot squared cosine squared phi. Whew. And that's just x2 dot. Still have y2 dot. So this is the parenthesis continued here, plus all right, this one's not going to be too different, too dissimilar. It's going to be L1 squared theta dot squared sine squared theta plus 2 L1 L2 theta dot phi dot. No.
Yeah. Yeah. You just replace the signs with the cosines in the second equation. Or why not?
Yeah. Sine theta sine phi plus L2 squared phi dot squared sine squared phi. See? No problem. All right, minus M1 G Y1, which is L1 theta dot sine theta. Yeah?
Shouldn't it just be L?
Yeah,
It's-
one minus cosine.
It's just Y1. It's just-
Yeah.
It's not.
Yeah, I was looking at Y1 dot, I don't know why. Yep, Y1 is L1, 1 minus cosine theta. Yep, thank you, sorry about that. Okay. Minus M2 G Y2, which is L1, 1 minus cosine theta, minus L2 cosine phi. And, oops, plus this L2, which is not gonna matter in the end. Woo, all right. We're pretty much there. We've got it on Lagrangian. Congratulate yourselves, we're almost done. Okay. I can't imagine how you do this. This would be so hairy in Newtonian F equals ma space. I'm trying to think of how you would do it. Right?
The answer is don't think about it.
Yeah, well, that's the advantage of Lagrangian. You don't have to think. You just plug your stuff in, you follow the math to where it goes, and you'll be all right. The problem is, in doing this in Newtonian approach, right, is the coordinate of this, the origin of this coordinate system is like non-inertial because it keeps moving back and forth, and so you have to account for, oh my God.
Well, it depends on it too, doesn't it?
Yeah.
The coordinate position of.
Yeah, that, right? Yeah, because this pendulum back affects the first. Seriously ugly stuff. So you think this is ugly? Try it in Newtonian space. Okay, let's do step 4. Apply our Euler Lagrange equations. Which are going to be that, so we got 2 coordinates, theta and phi. So we got a dl, d phi over here, I'm sorry, d theta is our generalized force, is equal to d by dt of dl d theta dot, our generalized momentum, and then that dl d phi is equal to d by dt of dl d phi dot.
Would it benefit us at all to go through and simplify that Lagrangian?
Oh, we will.
Okay.
Yeah. Should we do that now?
I mean, yeah,
Let's do that
before I
now.
start doing it, yeah.
Let's do that now. Sure. I'm gonna do this on the fly here, so that it doesn't screw us up, because otherwise we're just gonna run out of space on the board. Cosine squared plus sine squared is equal to 1, right?
Yep.
So this is just gonna be equal to that, right? There should be another one of those over here too, right?
It's the top, the very first
Well,
one.
there's the very
Okay,
first one.
have I blown this yet?
No, very good.
Okay.
And then the L2 phi dot. And
This
then-
one?
No,
No,
no.
to the right, to the right.
Yeah, so these two are the, yeah, this is
Yeah.
gonna be the same thing, right? Yeah. So that cosine squared plus sine squared is gonna be equal to that.
Yep. And then
Okay.
you can do it on the top one too, the 1/2 M1, because the cosine squared, sine squared there.
Oh, yeah. That's gonna make this much nicer. Boom. Not seeing anything obvious with this big ugly one. I bet if I knew my trig identities better, we could do something. Like, is this?
Yeah, I don't know that it would necessarily help it.
Yeah, well, the problem is that it's cosine, it's not like cosine sine, it's
Right.
different.
Yeah, but it's
Right.
this is probably, you know, cosine of theta plus phi over 2 or something, right?
That is good,
Huh?
Cosine theta, cosine theta. I don't know if it helps.
It
Probably
ends
makes it
up
more
being like
complicated.
1/2 times the quantity cosine u or
Yeah.
cosine theta cosine phi
Yeah.
minus whatever.
I don't think it's
I
gonna.
don't think it's not.
I don't think it's gonna help us
necessarily,
really, so
no.
let's just leave them. Okay, similarly, I don't think there's anything we can do with these really. Well, the G, 1 minus cosine theta is common.
Yeah.
Does that help us really?
I don't think you're gonna really accomplish anything with that.
I think we could shorten it a bit. We could make it different, but I don't think it's gonna really improve it. So let's go ahead and leave it at that. I'm gonna erase this and come back. Reuse this space. Since this can't go on forever. Okay, so start over here. DL, d theta. Let's go through. No theta's here, no theta's here. Theta, no theta, theta. So interesting, there were some thetas from the kinetic energy term, right? And that's because of this changing coordinate system where things are back affecting each other. So this is gonna be M2, and that 2 is gonna cancel. L1, L2, theta dot, phi dot. Then we're doing thetas first. Cosine of theta is gonna be minus sine theta. Let me take the derivative. Cosine phi. Okay. This other, similarly, we got this other term here, which is going to be looking somewhat similar. It's going to be plus M2, L1, L2, theta dot, phi dot. The sign is cosine theta sine phi. And that's going to be the left-hand side. That's going to be equal to d by dt of the generalized momentum, which is going to be this d by d theta dot. Did I miss something?
Oh yeah, we're not doing the bottom part, the M1 GL 1 minus.
I'm not done. Yeah, you're right. Yep. Okay. That was just the term that's unusual, that we don't expect to see. What about the term we actually do expect to see, which is minus. Okay, so these
Minus sine.
Yeah, we got 3 minuses. 1, 2, and then we take the derivative. It's gonna be another one. Minus M1 G L1 sine theta. And so, something somewhat similar for the other one. It's gonna be M2 G L. Oh no. M2
Yeah, GL1 sin theta.
L1 sine theta. And then this, you're right.
That's it.
So we're just doing the thetas, that goes away. Okay. Okay, so that's one side. That's equal to d by dt of the theta dots. So similarly, the theta dots, no theta dots down here, but theta dots everywhere else. But they're not all so bad. So this one's just going to be M1 L1 squared theta dot, right? Take the derivative of this with respect to theta dot. The 2 comes out, matches the other, it matches the 1/2. Plus, same thing here, 1/2 M2 L1 squared theta dot. But we got the fun terms. These aren't so bad. You just
Theta dot out.
take the theta dot out and you're done. So 2 L1 L2 phi dot. I'm just gonna call it that times cosine theta cosine phi plus sine theta sine phi. Right? Because the rest of those are the same. Plus an M2. Whoop. There's an M2 in it. No.
Theta dot, I think is 0, right? Or actually theta dot.
For this one, yeah, you're right. We're done.
Yeah.
This parenthesis closes that. Okay. All right, so we might only get to the, might only get to theta, because I don't want to hold you guys over, especially if you guys are here for the bonus round. I don't want to hold you more than I normally do anyway, which is already bad. Okay, so let's take this whole thing d by dt. So redoing this part, d by dt, this is going to become M1 L1 squared theta double dot plus M2 L1 squared theta double dot. So it's an acceleration plus
Yeah, that should
Well, I guess.
all this stuff's changing with time.
Yeah, that's true.
It's gonna be a horrendous product rule from hell. Okay, so we're gonna have 2 L1, L2, M2, phi double dot times cosine theta, cosine phi, plus sine theta sine phi, plus 2 L1, L2, M2, single phi dot times the derivative of that with respect to time. You guys drawing? Yeah. This is not, see?
I'm sorry, yeah.
See? It's such a simple problem, right? There's only 2 particles. Why is this so complicated? It's complicated.
Can I go back and say what proof?
Yeah. Yes, yeah. Yeah, right? It makes the proof look good by comparison. So we'll just finish, we'll get this close and I'll let you guys go. Okay, so this is gonna be, okay, theta dot sine theta cosine phi plus minus phi dot cosine theta sine phi plus theta dot cosine theta sine phi plus phi dot sine theta cosine phi. That wasn't so bad, right? Okay, so generally this is the equation of motion. The way to actually get to the answer here would be to
Solve.
yes, ultimately, but you know, plug it into a computer. But to make it a little cleaner before you plug it into a computer, essentially group the like terms. Group the terms for theta double dot, the ones for single theta dot. Which are there any theta dot terms in here? Here's one. Here's a couple. Theta dot terms, and then the theta terms, which is the rest of them. And then you do the same thing in phi. But what's nasty about this is, right, these are coupled, right? The phi one depends on the theta one, and the theta one depends on the phi one. Yeah. So that's why this is such a mess. But before you plug it in the computer, you have to be able to get to the equation of motion, okay? That's like this part you plug in the computer. So at least we get there, and no matter how ugly it is, the computer can handle it, as long as you don't write in a typo as you're doing it. All right, sorry I've gone over a bit, but we've dodged the bullet of the proof for now in favor of, now you know things that are worse things than proofs. Doing actually difficult, you know, like, this is just 2 particles, okay? But it's a nasty problem. So we will do some more problems and practice problems tomorrow morning, but they won't be this hairy, I guarantee you.
Throw the mass of the strings in there.
Yeah. Yeah. Little 1/2, you know, omega squares in there, yeah.
But, I mean, essentially all I'd do would be change L2 on the M1, because if you just treat just like the center of mass as a point in the middle of L1.
That would work for this, but then the moment of inertia is going to work the same way, yeah. Yeah, for a rod.
Want me to get
rotating
the-
rod set. Yeah, sure, thanks.
So are hanging or chains like the most chaotic thing in the universe?
The what?
Are hanging, swinging chains?